Hi, welcome to Mathematics with Tom. I am Tom, and today I want to talk about linearly dependent and linearly independent vectors and what they mean. So today let's talk about dependent versus independent vectors. So we're going to look at this as we're going to study our vectors as column vectors. So for example, let's suppose we have the matrix A, and the matrix A is 1, minus 1, 0, 0, 1, minus 1, and minus 1, 0, 1. Now, we're going to use formal definitions here in a moment, but I want to just use an approach that might be more easy to see. Dependent vectors are linear combinations of other vectors. That's all they are. So let's look at the columns of A. And so let's look at the columns of A, and let's decide are those dependent or are they independent vectors? So what that means is that if I take the columns of A, so I have 1, minus 1, 0, plus, and then I'm going to leave a little space here, and you'll see why, because we're going to put a scalar there. 0, 1, minus 1, plus, and we're going to need to leave another space for a scalar, and then let's do it this way. Sometimes people see it this way easier. Equals, and then I'll put a scalar there, equals this third vector, minus 1, 0, 1. And what I want to do is, in each of these orange boxes, what I would like you to do, and then I'm going to do too, is this. Find scalars, and I'm leaving them in orange because they go in the orange boxes. Find scalars that make the statement true. Find vectors that make that statement true. Well, let's take a closer look at those. Notice that if I take 1, I'm looking here, I'm looking at this very first row. So I'm looking at this first row of, oops, that's not a good notation. This first row here of 1, the 0, and a minus 1. So notice that if I have a 1, let me come back up here. So if I have some scalar times the 1 plus I have another scalar times the 0, this has to equal some scalar times negative 1. Well, if you take a look at it, my initial guess is that, well, the obvious one would be, what if we put a minus 1 in there? Let's just try it. What if we put a minus 1 right there? And then, well, we could multiply the 0 times anything. But let's think about, before we jump into this, let's look at the second row as well. So the second row says that the sum scalar times a negative 1 plus some scalar times a 1 has to equal some scalar times a 0. Well, if we look at this, notice that if I had a negative 1, I already put that first negative 1 in there. Let's just see if we can carry that through. So what if I put a negative 1 in this box as well? Because it has to be the same scalar on that first vector. Well, the first row works with a 1 in this position, And I'm going to leave this box empty because any number doesn't work on, will leave 0 the same. So now I've satisfied it. Well, let's see, I've got these boxes filled out. Let's see, can I make this work again? Well, -1 times -1, now it's a +1. What if I put a -1 right there? It would also work up above. Let's check and see with these two vectors, those two vectors, if it's going to work in that last position. So this is row 3 we're looking at now. So we're looking now at row 3. Oops. I'm looking now at row 3. And let's see, if I take that first vector and with a scalar of -1 times 0, plus I take another -1, that's my next scalar, times a -1, do I get a 1, that's my scalar, so put it in the box, times a 1? Oh, I do. Look at that. Look at that. Look at what we did. So let's write this down. Let's write this. So now I just found that if I take -1 times my vector of 1, -1, 0, plus, I have another -1 times the vector 0, 1, -1 equals the vector, oops, let me put my scalar in there, my vector of 1 times -1, 0, 1. So look at what we just did. We said that the third column is a linear combination of the first two. And you could have picked the first column and written it as a linear combination of the second two. The order in which you decide, which you might see the answer, doesn't matter. The end result is the same, and I'd like to show you why, because we are so close. So far we've established this. We've established our statement. Dependent vectors are linear combinations of other vectors. So right now, what we can say is we can say the columns of A, not little k, but the matrix A, are dependent. So now let's just do a little bit, a little work on this equation here. So I'm going to take this equation and let's just rewrite it. Let's write it as negative, let's set it equal to 0 on the right hand side. So -1 times 1 -1, 0 plus -1 times 0, 1, -1 minus 1, or plus a -1, minus 1 times -1, 0, 1. Well, what does that equal? It equals 0, or the 0 vector, 0, 0, 0, and that's just the 0 vector. Well, wait a minute. The left-hand side, we said that the left-hand side can be rewritten. We put the vectors into the matrix of A, so 1, -1, 0, 0, 1, -1, and -1, 0, 1. So we said that the vectors form the columns of A, and then the vector x are the appropriate scalars. So I have -1, -1, and -1. Well, notice what happens. Those give me the 0 vector. Now, you may say, okay, great, I solved it. But here's the interesting part of this solution. Remember back when you were solving linear equations, and then quadratic equations, and in calculus, when you had 0, if you had a number, say 3, times your variable x, and it equals 0, there's only one answer. There's x is 0. But wait a minute. We just said that the matrix A times x, which is -1, -1, -1 equals 0. Okay, and the 0 vector. So now we've just turned on its head all you knew about the product of two numbers being 0. In matrices, it doesn't work. Now, when x is non-zero, when x is not 0, or not the 0 vector, and ax still equals 0, then what happens? Then the columns of A the columns of A are dependent. Dependent. And this also means a few more things. It means that the A inverse does not exist. And for a matrix that has dependent columns, we call A, let's just this, A inverse does not exist, and A is called a singular matrix. I'm going to make that a capital S. It's a new vocabulary word. It's worth remembering. A singular matrix. So I wanted to close here, but there's two things. I'm not even going to go onto a new page. And here's the definition. If you have a scalar, say x1, times the first column of A, I'll write it this way, plus you have the second scalar, x2, times A2, the second column, plus, and maybe we'll just look at a 3 by 3, A3 times the third column of A. If the only way that those can give you the 0 vector is for A is for x equal the 0 vector, x equal the 0 vector, then the columns of A, are independent. Yes. So that's so for example, if I had 0 times A1 plus 0 times A2 plus some number like 3 times A3, and it still equals the 0 vector, those are not independent. Those are still dependent columns. It's probably not a very interesting matrix. It's probably A1 has numbers and A2 has numbers, and then A3 is probably just the zero column. So anyway, that's the point. Not until all of the scalars are 0 are the columns of A independent. If just one of them, like here, is not 0 in order to get to 0, then A is a singular matrix. I hope that helps. Thanks for watching.